Welcome back to the Foundations of Computational Economics course. In video number 14, we will be looking at Numpy library and talk about how vectorization is done with Python. Let me remind you that core Python only provides the basic functionality of the language, and to do scientific computing, we are pretty much all the time rely on additional libraries. And here's a collection which is typically used for scientific computing, including economics. Numpy is the library that facilitates vectorization. SciPy is a collection of useful functions that perform simple or common tasks needed for computation. Pandas is the tool to work with the data. Numpy is the library that provides the possibilities of just-in-time compiling of Python code into machine code that makes it very fast. We'll look at that in the course as well. And finally, matplotlib is the library that we've used many times by now. In this and in the next several videos, we will look at these libraries one by one. So today, the focus of this video is Numpy. Numpy is a very widely used scientific computational package. In fact, we have used it already, and we will use it pretty much all the time from now on. But today we'll see the details. There is a wonderful reference guide that you should go to every time you have any questions about Numpy. But the core message that you need to know is that Numpy is essentially an implementation of the vectorization for Python that is written in lower language code and therefore runs very fast. Let's just take a step back and remind ourselves how we include the libraries. So the standard way to do it is to write import library, and in this case, that's going to be Numpy, as reference. Reference is usually just a NP for Numpy, and it's a good idea to keep the common short nicknames for these libraries so that your code is readable by other people. And there are actually other ways to do it as well. So, for example, you can say from library import a particular function if you want to import the function. It does make difference on how we use the functions imported after that. So if we import a library as a Numpy, then we have to use the namespace of that library with preceding all of the calls to the functions of the library with np dot. And that is actually very useful because you then remember, for example, something like this would be different from just saying maximum. You will remember which library function you are referring to because libraries do introduce differences in Python. Let me run this and import Numpy. And let's just start with an example of how powerful this vectorization technique is. In this little code, for a very long list, I want to calculate the mean of the list, the average value. So let's first look how it would be done in native Python. And probably a good way to do it is to call range and create a list from the range of these numbers. So these are going to be all the numbers from 0 to n-1, as you of course know. And then I want to time the call to the function sum, which sums up the list and then divides by the number of the elements. Okay, that'll give us the mean. With Numpy, what we will do is we would create what's called an Numpy array from the same range of numbers, and then we will time the function that belongs to Numpy, and it's called mean, that can be applied to the array directly. That's essentially a method of the Numpy array. And let's compare the times. And here we are. You can see that the native Python took about 5.74 milliseconds, where Numpy took less than a millisecond, 7 times faster. And this is not surprising. As I said, Numpy is implemented in a low-level language, and therefore, if this vectorization is possible, and if we can represent the things that we want to do in terms of vectors and matrices, then we definitely should use NumPy and use these techniques. All right, so let's talk about how this is organized. Well, if you remember, we started talking about Python in the beginning from a list of variable types and talking about what kind of variables there are in this language. We are kind of forced to do the same when we look at NumPy, and more generally, I can say that knowing Python is not enough. To be a good programmer in Python, you have to actually know Python libraries that you're working with. And a library like NumPy would introduce into the language new objects and new data types and new methods. So in NumPy, we are going to sort of more detailed representation of numbers. There will be C language-like types of int of different lengths. Numbers here refer to the number of bits which are used to represent a number, and uint versus int, that's basically a difference between unsigned integers and signed integers, where uint spans the numbers from 0 up to 2 to the power of the given number, whereas the simple int spans 1 bit for a number, and therefore it goes from it's half of the representable numbers are assigned to the negative values. And the same thing with float. You can have different kinds of float which take different amounts of memory. There is a link here to all the data types that are representable in NumPy. There is a number of them, actually. And there are some differences between the way that NumPy works with numbers and variables and how core Python does the same. Okay, let's look at some examples here. np.array, as you have probably guessed already, is the command to create the np array, the main data structure, which is made available by NumPy library. This is going to be the array that represents the vector matrix that we want to work with. When we create the np array, we can give it a list of values, and then optionally we can set a particular type for each of the elements of the array. You can see here that I'm converting this integers to a Boolean representation or an int representation or a float. If we run this, I want to look how much memory each of these representations take. This is just an array of 3 elements. And you can see that the Boolean takes the least amount of space, and then int 16 takes more, and then float 64 takes yet more. And this is expected, right? This is expected because we are assigning to use different number of bits to represent a number in each of these specifications. The main message here that is important to understand is that NumPy prescribes the same data type to all elements of the array. So unlike lists in Python, NumPy, the elements of the NumPy array cannot be of different types. They all are prescribed a particular type that this NP array has. Now, some things, like I said, are different between NumPy and core Python. And if you remember, in core Python, an integer didn't have the upper bound. We could store any number, any value in the integer variable, and Python would allocate additional space as needed if the variable was too large. Well, that's not the same in NumPy. So look at this. What I'm doing is that I'm creating the array of 3 zeros, and I'm prescribing the type of unsigned integer with 8 bits to be stored in each of the elements of this array. And I'm saying that the first element should be 255, and then the second and third elements are just increments of the previous element plus 1. What do we get? Well, we should be a little bit surprised. 255 plus 1 is 0. 255 plus 1 and plus 1 again is 0 again. What do you think is going on? I'll give you some seconds to think about that. Well, right. So the unsigned int of 8 holds numbers between 0 and 2 to the power 8 minus 1. So this is just a pure binary representation of numbers here with 8 bits. And of course, the maximum number it stores is, in fact, we can just say 2 to the power of 8 minus 1, and that's 255. So that's the maximum number that this data type can actually have. And if we add to that, what happens is that we get an overflow, but there's no error because the yet another digit which doesn't belong to this number is turned to 1, and all the rest of them are become 0. It's like adding 1 to 99, you get 100, right? 3-digit number with 2 zeros in the lower two bits, and that's exactly what's happening here. Now, what happens if I set this to uint16? Then we wouldn't have a problem, right? Because now we can represent numbers up to 2 to the power 16, and then 256, 257 clearly fit in. Now, what's the maximum here? Let me look at that. It's going to be 65,553, and sure enough, if I put this number here, then we get overflow as well. So that's one thing to be aware of. And why is Numpy doing this? Well, very clearly, Numpy is giving us a lot more flexibility in how we manage the memory in the computation. And if we know that the problem that we're solving does not require large numbers, then we don't want to spend memory in storing this not so large numbers in potentially large arrays. So Numpy is sort of like a step towards the lower level control of the computer hardware. So infinity and not a number are, of course, also used in Numpy as part of the float. But the behavior is slightly different, again, to the core Python. Look at this code here. We've created an array of -1, 0, 1, and 10 of the type float. And now we want to divide x by 0, and that's basically dividing element by the array using element by element type of operation. So we're dividing by 0 each of these numbers. And you can see that there is no error. Actually, Numpy creates this vector with -infinity when it divides the negative number by 0. Nan, 0 divided by 0, into infinities. The only thing that it also prints this warnings, the runtime warning, divide by 0 encountered, and again, invalid value encountered in true divide. Well, if we try to do the same in core Python, and here I'm just saying that y is an integer 10 divided by 0, we get a division by 0 error. If that's a float, we still get a float division by 0 error in the core Python. In Numpy, we actually have a way to deal with the warnings. So, for example, if I say just ignore this division by 0 issues, then we clearly just get, cleanly get the vector with infinities and nons. And that's quite handy in many computations. Now, it's important to be aware that the infinity can be compared to itself. So, just since we're talking about these numbers, strange numbers, let's highlight that comparison will go through, but you cannot compare nan to nan. See, b turns out to be false. And that's because nan is defined in a way that, it's something that is different. It's not a number, but it's a different not a number, at least potentially every time. So the right way to check whether something is or is not nan is to call the numpy function isNan, which returns none, returns true, I'm sorry, if it's called with a not a number. Okay, so what's inside the array? Let's go back to our object explore function, which I now have included into this static directory that would be available in the Git in the Git repository of the lecture slides. And to make it accessible to the Jupyter notebooks, we want to extend the path for the notebook and insert this directory in there. That's why we need this 2 lines of code here. And then we can just import, and look how I import this library. Now, any .py file with functions or classes or any other Py code can be a library, can be also called a module, and we can include it just the same way as NumPy, except here I don't want to say object explore every time when I call this function, because this name that I just highlighted here is actually the name of the module, and then we would have to have that dot and then the name of the function, which is the same. So here instead I'm just importing everything, all of the functions, so that we don't have to call them with the prefix of the name of the module. All right, so now I can call, after I ran it, I can call object explore directly. Well, let's create this NumPy array again, and for all elements I want to print the type of the element. And as you can see, this is the NumPy representation of float 64. This is a float number which takes 64 bits of memory. And then the A can be represented, the NP array has a representation which looks just like that. You can see that 1, 2, 3, 4, and 5 are floats here. What about A range 5? By the way, A range is a NumPy function, which is similar to range, but it creates an array of numbers between 0 and up to and excluding the upper bound that we give here. I'm having +1 to get an array of 1, 2, 3, 4, 5 instead of 0, 1, 2, 3, 4. Okay, now this is also an NumPy array, as you can see, and the type of it is unsigned integer 8, as we've asked for it. So this illustrates that the type of the NumPy array is the same in each of the elements of the array. NumPy array is everything else in Python is an object, and we can explore the methods and properties of this object. And you would see by calling object explore that there is quite a list of publicly available public methods for the arrays and also the properties. The private number of methods is even larger. And so as you remember, this double underscore methods, they implement some sort of standard operations on the array. Besides our homemade object explorer, it's quite useful to actually call help on the object, on the instance of the class NumPy, that gives you the information of what can happen, what you can do, and what you can access about this arrays. Well, I'm not going to spend time on reading all of this. You can do it yourself as an exercise, but we will see in numerous examples throughout the rest of the course how we're using NumPy arrays. Okay, just to also drive this point home, let's look at the memory usage of NumPy objects. So here, this little function essentially creates a dictionary. Dictionary is another native data type where we have a collection of lists with their each particular name, or key as it's called. And here, this function basically creates a dictionary that in a number of steps grows, increments some variable, and we're collecting data on the size of the variable in the memory. We did something similar in one of the first videos. So here's what I want to do. I want to take a Python list And the way it's going to grow is that I'm going to be doubling the length of the list every time. This is going to be given with this lambda function. Remember that, it's going to be a list of zeros, but the multiplication means that we want this list to have a particular length, and the length is going to just double every step. We're performing 10 steps of this doubling. The NumPy array will grow in a similar way. We will create the NumPy array from the list that grows in the exactly same manner, except that I'm using the x.size method of the NumPy array when calculating the size of this instead of length x. And then to make the results visually appealing, we will create a simple plot. And as before, I'm using matplotlib library without even yet telling you what that is. But in a video, we'll be talking about graphics in a lot more detail. But here we're just plotting a couple of lines and giving it some labels in the legend. Let's see, what do we have here? You can see that the Python list, let's look at the axis first. Steps of the variables, of the variable updates. So we performed 10 steps, and we can see how the size in memory grows as we double the length of the array, or of the NumPy array, or of the list. And as you can see, the Python list grows in size much faster than the NumPy array. And that was the whole point of talking and defining all these different data types that I've just talked about. As said already before, NumPy provides more control over the variables and over the size and the memory that it takes. So here's a little exercise. Clearly here list takes more space, and that's probably because we're using int 8 for each of the elements of the NumPy array. Can you make these two lines overlap somehow? Think of the way. Here we go. And the way I wanted you to think about that was that we can actually change the data type of the NumPy array and say, for example, we can change it to 16 bits per element. And I think these two lines are becoming closer. What about 32 bits? Yet closer. And 64 bit, and they are overlapping. So it tells us that Python by default is storing the integer values in the same amount of space that is 64 bits per number, and that could be that is a lot of memory, and that could be too much, and you could be wasting memory with lots of zeros if you're not working with numbers of that size. And so that's why NumPy allows you to have greater control. All right, how do we create arrays? Well, we've seen already how we create arrays from lists by just calling the initializer of the subject NP array, and that's probably the easiest way. But there is also a bunch of functions that create lists of particular type. For example, you can create an empty list, and this only allocates space without initializing the space in the memory. You can have a list of zeros, of ones. You can have a range, as we've seen already, which spans the numbers from 0 up to the bound. Or a very useful command here is a linspace, which fills linearly with a given number of points the space between given bounds. Okay, let's do all of these. So look, zeros are initialized to zeros, ones are initialized to ones. By default, they become floats, right? That's indicated by this dot. The A range is a range of integers, which are a NumPy array, which are organized in a NumPy array. And you can check which default type is used for these numbers. And linspace, as you can see, fills up the space between 2 and 3. These are floats. Now, I skipped the first one. What do you think these numbers are in the first list, which we initialized as empty? Well, they are basically garbage, and if we run the code again, they actually change, as you can see here. More interestingly, if we prescribe different number of space or different amount of space to each of the elements, they change quite a lot. And what's going on is that, as I said, because this list is not initialized, just allocated space, it could be that that memory, which is allocated to this data, had some values there already from previous operations, and that's what we get. It's some garbage in the memory that we see when we are running empty. So the bottom line, if initializing lists is efficient, or it's a step towards efficiency, it's always better to allocate memory once before you start, say, a large loop, if you need that memory, other than reallocate in each iteration of the loop when you calculated yet another value to add to a big list. But you have to be aware that that it's possible that this memory is not initialized. And this is, of course, faster than calling zeros, because zeros has to go through that list and assign zeros, initial zeros. Okay, let's look at the matrices. Similarly, there are commands to create a matrix, create matrices with NumPy. And I being an identity matrix ones, which is similar to the ones that we saw here, with dimensions given as a tuple, creates a matrix, creates a two-dimensional array, as seen here. So here's our A, that's an identity matrix. Here's our B, which is the matrix of ones. Now, you can see that this is represented as a sort of a list of lists. Well, it's not a list, it's an NumPy array, but the point here is that the data is stored row-wise. So the first, we first store a row, first row, and then the second row, and so forth. And this is different from some other languages. You could store it by column as well, but this is the way that NumPy is doing it. We can do things with matrices. For example, we can add a scalar to matrix B. When we print B, it becomes all threes, right? There used to be ones, plus 2 is all threes. These operations are by default element-wise. Now, I've said that I've asked for the type of B, and the type of B is ND array, so NumPy array, although it is a 2x3 array, two-dimensional array. Here's the command that converts an array into a matrix. NumPy has an additional a class to represent objects which are matrices. The difference between matrices and the NumPy arrays is slight but important, and matrices are initially made to simplify matrix operations and working with matrices in general. Now, unfortunately, they're phased out, or maybe fortunately, to skip the confusion, so we will not pay too much attention to them. But here's the matrix, and you can see that C is a matrix with the same data but different type. Okay, what we can do with matrices? B was just a 2x3 matrix filled with value 3, and if we multiply B times B, what we get is an element-wise multiplication. Remember, B is an ND array, so NumPy array. If we do the same with C, we get an error. What's the error? Well, the shapes are not aligned. You cannot multiply 2x3 matrix by itself without transposing one of the components, one of the elements. And this is one of the difference between matrices and ND arrays. What do we do instead? Well, we can transpose. And to get the same result for B, we have a special operation, which is the add sign, which is the matrix multiplication for an array. And here you can see that it also gives us the mismatch. dimensions. So we have to transpose B as well. Transpose. There we go. All right. That's a bit of a difference between matrix and ND arrays. But like I said, we will be primarily working with ND arrays. Now, the next big topic is how to get access to the elements of the ND arrays. And here there are some variety of ways. So we can index the elements of the ND arrays by scalar indices, by just giving the address in the array. It could be one-dimensional, two-dimensional, or multi-dimensional, in fact. And this is the same as calling the get item private method of the ND array. We could slice arrays also in multiple dimensions, similar to what we did with strings or lists. We can have numerical indexing into the arrays. Let's look at that. And we can do masks, so logical indexing. Here's a little bit of a code for as an example. So Z is the lin space. Initially, if we print Z at this stage, you can see that this lin space is just a raw vector. It's I should correct myself. Numpy has vectors represented by one-dimensional arrays. So at this point, we can't say whether it's a row or column. It's just one-dimensional array. Now, when I reshape it, I create a matrix out of this array. And here's the matrix. Can I highlight it? There it is. And you can see that we filled this matrix row-wise with these lone row values that Z used to be. And how is this reshape done? Well, we are creating something by 5 by 3, a matrix 5 by 3, so it's going to have 5 rows and 3 columns. Of course, we have to give it the correct dimensions to fill out the array, but there is a shortcut of saying that we want one of the dimensions to be whatever it needs to be to fit the rest of the to create the matrix of the right size. So -1 means calculate the other dimension yourself. Let's see how we can index into this matrix now, into this matrix Z. Let me first comment out all of these. Well, first, what's Z of 1? What's Z of 1? You can see that unlike what we could have expected, it's not just one element. It's actually a row. And this is the row number 2. It's the second row. Well, it turns out that if we index using just one element, we're indexing rows of the two-dimensional array. And then, of course, because the indices start with 0, we get the second one. What about this notation? 1, 0. Well, then we get a one element, which is this element here. Now, how about slicing? -1 colon. What does it mean? It means that we want the last element and start with the last element and then go till the end. So it's basically just one last element that we get, and as before, it's a row, and so we have the last row. Observe, though, that here, unlike in the first example, the row was in the single brackets. So that means that the row was returned as a single dimensional array. Whereas with slicing, you actually get the double brackets. So this is a two-dimensional array in which the first dimension is simply 1. And that might be important for the linear algebra expressions. What about this? Example here? So here we want the first up to the third row and the first element of the row. Let's see what we get. So the first 0th 1, 2, 3, that's this subset. Oh, of course, excluding 3. So 0, 1, and 2. And then we want the first element within this matrix on the second axis. So we should get, this is 0th. And so we should get this 0.57 and 0.1. And that's exactly what we get. And again, observe that this is a one-dimensional array that we have. What do you think we get here? So that's, again, the row is going to be 1 and 2. And we want the elements from indexed 1 all the way to the end. So we should get this same matrix here, and it should be 2 by 2. That's exactly what we get, right? So that's from here to here. Finally, a final example is just a column means that we want all of the rows, and then the first element that would be the column index. So we should get just the second column from this matrix, and this is going to be exactly what we have. Now, how do we change this code so that we have the column as a column vector rather than a one-dimensional vector? Well, remember that slicing preserves the dimensions, and so we should just simply slice the column from 1 to 1, from 1 to 2 rather, and that means that we take the index 1 and all the way up, but excluding the upper bound, and that gives us the column from this matrix as a column vector. All right. Using this, since we can access different elements of the array, we can assign these elements. And so here, for example, oh, I should have done it in a different way and didn't run all of this. So let me go back and rerun RZ. The element 1, 0, so on the first axis 0, 1, 1, and 0, it is becoming -1. Okay. Now, what do you think this will do? Because this is accessing the whole row, then we should expect the whole row to change, and that's exactly what we have. What about now? So these are all of the elements in the column, and it's going to be the first column, and we're giving 1, 2, 3, 4, 5 numbers. So we are replacing the first column with the given numbers, and that's exactly what we have. Next, what about this expression? So here we want to access from the beginning up to the second, or the element index second in the rows, and the first element there. So somewhere in the second column, we want to put 9.3, and probably it's going to happen with multiple elements. Let's see. And indeed, it's going to be in 0th in the first row in the second column. And that's there we are. Very well. And finally, this is the double bracket indexing. We get a -2 in the indexed third column and third row and second column. And this is another way to access elements of the Numpy array. Essentially what happens is that Z of 3, that's the fourth row, and then in that array we're indexing the first element. Some more examples. Z is now a lint space between 0 and 2 with 12 points, and we want to reshape it to the matrix of 4 by 3 and print. Now indexing, so here's our Z. Indexing element by element with numerical index, that was our third way of accessing elements, numerical indexing. So here we are giving Z 2 lists. So this is first list and this is another list. of the indices of the elements that we want to put into the new array. And so the first element is going to be 0, 0, and this is this one. The second element is going to be 2, 1, so 0, 1, 2, 0, 1. So it's this one, and you can see that this is the second element of the printed out list. And the third element will be 2, 0, 1, 2, 0, so this one. So as you can see, we've created the list of 3 elements. It's a NumPy array, not the list, of 3 elements, which we sort of picked out of the matrix by giving explicitly the addresses of these elements. We can use Boolean expressions as well. So z from such that z is greater than 1 is going to give us a one-dimensional array of all of the elements in z that are greater than 1, and they're all here. So we have 1, 2, 3, 4, 5, 6 elements in this new array, which is printed. We can also have something called a mask, or we can store the conditions for the selection of the elements from the NumPy array in a separate NumPy array. And here we're using the command logical AND. This is element by element logic with 2 conditions. So we want the elements to be between 0 and 1.75. Between 1 and 1.75, sorry. And here's our mask. And you can see that it's false everywhere in the first 2 columns, and it's true in all of the elements of the third row, and only 1 true in the last row. So this is the way how elements of z might be selected. Of course, those selected will be on the true, corresponding to the true values. And here we are. So we are selecting completely the third row, and there it is, and 1 additional element from the fourth row, and there it is here. So these are all the ways to index into the NumPy arrays, and as you can see, there is quite a choice. Let's talk now about the operation broadcasting. This is a very powerful technique that is implemented in NumPy as long as other languages working with matrices and vectors. And what it is essentially is that when you're operating on 2 NumPy arrays, if their dimensions differ in one of the axes, then the smaller array is automatically broadcasted along that axis. So if you have as shown on the picture here in the first row, if you have a vector plus a scalar, then scalar is automatically broadcasted to be added to each element of the array. And this is something that we are very familiar with. This is a natural thing to happen. Now, if you're summing up a matrix of 3 by 3 and a vector of 1 by 3, okay, then the 1 by 3 vector is broadcasted to fill out the matrix so that the operation can be completed element by element. And finally, if you have 2 vectors, one is a column vector and one is the row vector, then you can still add them up, and they're both broadcasted in the corresponding directions. And this third case is something that we'll be using in the course quite a lot, actually. And this is what allows the vectorization of the code to be done neatly and concisely. Let's see how it works. A is a ND array of 1, 2, 3, 4, 5, 6, and let's see what the operations give us. A plus 10, 10 is broadcasted, so we have 11, 12, 13. A plus B is element-wise, so 5, 7, and 9. Now, here X is a vector. Oh, it's one-dimensional. Again, look at the number of brackets. This is a one-dimensional array. It used to be 0, 1, 2, and we added 5. Y is the 3 by 3 array of ones, so this is a matrix. And if we add them together, this is printed here, then the X array is broadcasted along the vertical dimension. Right? So we have 6, 7, and 8. Now, could we broadcast it along the horizontal dimension? So along the vertical dimension, that's dimension 0, and could we transpose x before we add them to y? Well, no, and this is oh, I forgot the brackets. No, nothing changed. Why is that? Well, see, X is a single dimensional array, so a transpose doesn't change it in any way. So in order to transpose it, we should change it to the array which is 1 by something. And one way to do it is to reshape to which dimensions? 1 by 3. And now you can see that x becomes the row vector, and it is, since we transposed it, now the transpose makes a difference. It's added sort of vertically to the matrix of ones. There's another way to achieve the same. So here x is an A range up to 5, and we can reshape it as I did before, or we can index it in a special way, and Numpy has this shortcut called np new axis, which is essentially saying here that we want to take all of the elements in the array, and we also have this additional axis that we want to arrange these elements along with, and it just creates sort of an additional axis, right? So from one-dimensional array, x becomes a two-dimensional array of 5 by 1, and it's printed here. So now we want to transpose x, and that's a transpose, and x plus x transpose, that's going to give us the third case on this diagram, and we should expect an 8 over here, right? Because that's a 4 plus 4 and a 0 over here. Okay, what do we have here? X again is a matrix 3 by 4, and Y is a one-dimensional array. If we add them together as before, this is going to be added along the 0th dimension. Okay, we had this example already. Okay, just to say that, of course, broadcasting is going to work not just with the addition, it also works with subtraction, multiplication, division, integer division powers, and many other functions, which are called universal functions. This is a whole collection of functions provided by Numpy, which support broadcasting. Here's a big list. Broadcasting is something that we should expect from Numpy. And we should expect it to work with many different functions. And it is an efficient way to do things, right? Similar to the example in the beginning of this video, we can run some comparisons of the runtime. It's very similar. It's just that the n is a little bit smaller now, and that's because I want to calculate the sign of x on the list, which is given by a native Python list or NP array here. I'm using math library for the sign of the list elements here, and NP sign, the implementation of Numpy. Here you can see how the namespaces of the functions are important. These are actually two different functions achieving the same things, but NP sign, so Numpy version of sign, this is a universal function which supports broadcasting, and it can be applied to all elements of the array in one go, in just writing this instead of the list comprehension as we do here. And list comprehension is probably the most efficient way to do it with native Numpy, with native Python, I'm sorry. And you can see here that this test shows us that Numpy's way is about an order of magnitude faster. Reduction operations are those which change the size of the returned array, and this is basically calculating different statistics from a matrix or from the data in the matrix. again, there's a list of functions that are supporting this reductions, or which serve as reductions. Here is an example. We have a 4x3 matrix again. Here it is. It's called an X. We can sum X, and this is just the sum of all of the elements in the array. But we can also sum X along the first axis. The first axis is, of course, the horizontal one, right? Because the first, I mean, axis equals 1. Because the first one is indexed 0, and the second one is indexed 1, the Numpy way, base 0 indexing. And so we are summing along the rows. We can also have this reduce command, which can be applied to many different functions as well. And here I'm reducing using maximum. This is element by element maximum. And I'm reducing the X array along the axis 1 as before, so horizontally. And here's an additional parameter here, additional argument, which says keep dimensions. So as you noticed, when we summed the array even along the second axis, we get a one-dimensional answer. And this may be a little bit less convenient for linear algebra. Imagine that you want to multiply a matrix with this vector later on, and you want to keep it as a column vector. So keep dems allows you to achieve just that. And you can see that here the result is in a column. All right. Here's another example, and we're calculating the min along the second dimension in the three-dimensional array. So you can see here that now I have numbers up to 24, and I reshape them into 3 dimensions. This is now a triple bracket array when it's printed. So this is the whole array X. And we can do things like calculating the minimum along the second axis. Second axis is essentially the one that goes from this matrix to this matrix. Right? That's the last axis. The result that we have is has a shape 2x4. So we've collapsed the third dimension, and we are left with 2x4. And 2x4 result of this minimum is printed here. Let's see how it's done. It's dimension 0, 1, and 3. So the minimum would be between. No, let's be careful here. So it's 2x4. So the minimum is taken over each of the rows of the of these two matrices. Well, and that's quite right. So when we reshape, remember, if we reshape into a two-dimensional array, then the last dimension is filled first, right? And so here it's the same thing. The last dimension is filled first, and so we have a minimum over the what appears to be rows of these two matrices, and this is just the way it's printed, right? It's actually the third dimension that way. Okay, now we can also make, say, the mean over 2 dimensions, and then the result is going to be a one-dimensional vector, 1 dimension with 2 elements in that dimension. So we are taking the mean over the axis 1 and 2, so there's only 0th axis that is left. Wonders of multidimensional matrices here. Another thing that we should be aware of with Numpy is how Numpy works with memory. The thing is that it tries to conserve memory, as we've seen before, but it also tries not to copy data unless it's absolutely necessary. So whenever it's possible to maintain some simple pointer arithmetic, then the data in the arrays is generally not copied. So slices, for example, where we're essentially saying that take columns and rows of this matrix using this formula, starting here with this step and ending there, then generally data is not copied in that case, and that can actually lead to some interesting behavior. But if we are using numerical indexing or logical indexing and masks, then the data is generally copied. Well, how to tell whether it is or not? There is a property flags of the ND array that we can check, and there are methods to actually make explicit copies if we need them. So let's look at the example here. We're going to have again the matrix of 4 by 3. It's a two-dimensional array. Let's print it. And what happens then? I say that y is going to be a slice of x, and the slice is here, right? I take all elements along the 0th axis, and I want just one element between 1 and 2 exclusive on the second. So it's a second column of the matrix, essentially. Then I want to look at these flags of this new array y. You can see there are several flags. We're interested now in whether it has own data, and it's false. So that means that the data is not copied, and in the same time it's writable. So the data still belongs to the matrix X, even though y has access to it. And so then if we say y of 0 equals 999, y of 0 is going to be the first row of this column vector. And we are changing it. And as you can see, then we're printing x. The data actually changed inside of x. So y serves as a, you could say, a pointer to some data inside of x that provides access to x. This can be useful, but it also could be confusing. What do we have here? So here, y is, again, referencing something or pointing to something in x, but this time we're using this numerical explicit indexing. So y is 0, 5, and this is 0, 0 and 1, 2 elements. So 0, 0 is this one, 1, 2 is 1, 2, and 0, this 5. In X, right? Now if we look at flags, we can see that the own data is true. Data has been copied. And therefore, as we change Y, then print X, nothing in X has changed. This 0 and this 5 are intact in the X. There's an explanation of what flags mean and how to use them. We can look at them one by one if we need to make a check in our code. All right, let's look at the applications of Numpy. And of course, the most straightforward is linear algebra, working with matrices and vectors. And Numpy does provide a submodule called numpy.linalg, which has the methods like matrix decomposition, calculation of eigenvalues, determinant, ranks, inverses, and solving system of linear equations. So, and I guess it has also much more, which we can see by calling the object explorer of the linalg class. Look here that I import linalg as a separate name. Otherwise, we would have to call numpy or np.linalg the method. All right, a few examples. Here's a matrix. We can code it up like this, right, and print. And make sure it's the same. It is. What do we do here? Well, we are illustrating a transpose effect. We can calculate matrix rank. So all columns are linearly independent. We can calculate the inverse. We can calculate the determinant. All working beautifully. Let's remind ourselves that element by element multiplication here is working as we would expect from element by element, and then matrix multiplication requires the matrices, of course, to be correctly sized. Now this dot capital T is the same as saying transpose, just for shorthand notation. Let's look at a system of linear equations. I believe this is the same matrix A that defines the system, and we have a vector of B composed of 5, 5, 0, and minus 3. We have 4 variables, 4 equations, so it's well-defined system. How can we solve it? Well, here's B, and then we just say in peeling alg solve A, comma B, and we get a solution. As simple as that. I'm checking the solution to see that AX minus B is indeed very close to 0. In fact, it's down to machine precision. As we remember, 10 to the minus 16 on the 64-bit computer is the delta, the smallest sort of difference between the float numbers, usually. Now, what if we didn't have x4 with the same equation? So we would have an overdetermined linear system of equations. Can we try to solve that? Well, it turns out that yes, there's LingAlg has a method called LSTSQ. So this is a least square solution. That's the solver which minimizes the square deviation of the AX from B. And with a simple code where I'm recoding A, here I'm doing it the same twice, right? Yeah. The difference, as you can see, is that here X is not just a point, it's actually a tuple, or even a dictionary, where the solver returns many different things. It must be a tuple. Here I'm using this little trick here, saying that I don't want anything from the outputs other than the first output, and then I can treat X as a solution, as an Numpy array. Here's the solution. And checking how far we are from B, well, that's how far, right? But this is the best we can do with this system, where there are more equations, as you can see. There are more equations as variables. Finally, let's look at very simple application to economics. I want to think about the market equilibrium where supply and demand are linear functions. So in a simplest example, that would be the very simple Marshallian cross of supply and demand. We have prices and quantities. Let's assume that there is an n goods in the economy. The demand is given by some matrix A, the off-diagonal elements of which correspond to the cross effects between different products. And there's a constant, or a vector of constants. The supply is given by this equation with its own matrix B. And we want the supply to be upward sloping and demand to be downward sloping, so we will impose the positive and negative semi-definiteness of these matrices. The market clearing condition is, of course, just D of P equals S of P. And let's try to code this. Well, here's a little function that ensures that the matrix that it produces is positive or negative semi-definite. And it's going to be just a random matrix. So I'm using here the part of Numpy called the submodule called random, which provides the uniform distribution in this case. Let's not pay attention too much on these lines here. That's, I've explained what it does, and we will look at the random numbers in one of the future lectures and videos. 3 products on the market. I want to generate some slopes for the demand, and same thing for supply. And then to solve for the market equilibrium, of course, I just have to rearrange the matrices and the constants to ensure that D of P equals S of P. So we have A minus B equals S minus D. And that's exactly what I have here for the matrix defining the system of linear equations on the right-hand side. So if I run this, this is what we have. Here's matrix A, here's matrix B, and here are the equilibrium prices and quantities. Well, you may be surprised by a negative price here in the equilibrium, and that's essentially a virtue of this simplified model. you know, oh, there are negative quantities as well. Well, it turns out that, you know, imposing positive or negative semi-definites, definite form of the matrix is not enough to ensure that the prices and quantities in the equilibrium come out to be positive. But we may be lucky, and you know, we're working with random numbers here, so maybe these numbers which are generated for the slopes of the demands and supplies are not making too much sense. So this is not a perfect model, and yeah, linear systems in economic models, they're probably just for illustrative purposes. But here's a case where all the quantities and the prices in the equilibrium do come out to be positive. Okay, further learning resources on Numpy. Of course, the reference manual for Numpy is probably the source of all of the exact information. A few chapters in the Kevin Shepard's book are worth reading. And then, if you prefer the video format and you have time, here's a wonderful lecture on Numpy, on a tutorial rather on Numpy. Finally, if you want to refresh your knowledge of linear algebra, there is a wonderful visualization of different concepts in linear algebra provided by the YouTube channel 3 Blue 1 Brown. Seriously recommend that. See you next time.